Good morning, class. Gonna wait for some more people to join us. Hope you had a nice weekend. Good morning. Hello. Dum-de-dum. Good morning. Everybody's saying hi this morning. That's nice. All right, I think we have reached critical mass, so I'm going to begin. First thing I wanted to say, hello, is hello. The second thing I wanted to say is make sure if you guys have any questions for me that you ask them kind of before. Knock it off, Bug! Bug! He's barking at someone in the backyard. Make sure that if you have a question for me, that you ask it before Friday afternoon or Friday night. I got a couple of messages from not I don't even know if I got any from this class, but I just got a couple of messages about the assignment that was due Friday night, like on Friday afternoon or Friday evening. And generally speaking, I'm not checking my accounts for messages during the weekend. So just be aware of that. If you want to get in touch with me, you kind of got to get in touch with me before I go AWOL for the weekend. Okay? All right, so I'm going to get started today with our lesson. The title of today's lesson is Types of Forces. Okay, so there's a list of, I think, 5 different forces that we're going to learn about today that are commonly seen in physics. Okay? So some of the different types of forces that we will encounter. The first type of force that I want to talk about is just called an applied force. So an applied force is simply, and I would typically denote an applied force by F sub A, and it's basically just an unspecified force. Okay? So anytime you have a force where the origin of that force isn't really stated, we just call it an applied force. Okay. So there's nothing really to that one. There's the next type of force I want to talk about is called the weight force. Okay. And the weight force is the force due to gravity. Okay. It points downward because gravity points down. And yeah, so there's a formula for weight force, and it is m times g. So m is the mass of the object, and g is the acceleration due to gravity. Okay. So for example, if you had a 5 kilogram mass on Earth, it would have a weight force of 50 newtons, because that would be 5 kilograms times 10 meters per second squared, 5 newtons, or 50 newtons. All right. So I want to talk a little bit about what is the difference between mass and weight. Mass is essentially a property of the object. Okay? It's a measure of the amount of stuff, the amount of matter in a thing. Okay? Weight, on the other hand, depends in part on the environment. Okay? Through the acceleration due to gravity. If I take you and I transport you to the moon, let's say I teleport you to the moon. On the moon, you have the same mass as you have on Earth. However, you have a different weight because the acceleration due to gravity is different on the moon. Okay? So your weight can change from place to place because the acceleration due to gravity changes from place to place, even though your mass does not. The things that would change your mass would be if you ate stuff or you outputted stuff, etc. Okay? So that's the weight force. The next force I want to talk about is something called the normal force. And the normal force is the force preventing objects from passing through a wall or the floor. So if you come into contact with any hard surface, the force that resists you is called the normal force. Okay, so it's a force of contact. Anytime you're in contact with a surface, there's going to be a normal force present. All right. A couple points. In the IB exam, they call the normal force the reaction force. Okay. I don't know why. The thing about the IB exam is that they like to take a lot of sort of unique perspectives. I think to sort of be different. And the rest of the universe calls it the normal force, but the IB exam just says, we're going to call it the reaction force, okay? Because we're IB and we're special. So, anyways, so I'm going to teach it as the normal force because I've never heard it called anything else except for within the IB exam. The variable that I will use for the normal force is F sub n. I believe the IB exam uses R for reaction. Okay? It points perpendicular to the surface. Okay? So if you had a floor like this, then the normal force that the floor exerts is going to be away from the surface, okay? If you had a ceiling, the normal force that a ceiling exerts is going to be away from the ceiling. If you have a wall, the normal force that the wall exerts is going to be away from the wall. So the normal force always points perpendicularly away from the surface, okay? So we're going to do a couple of examples with normal force here, all right? So what if we had a 3 kilogram box that is sitting on a flat surface, okay? What is going to be the normal force in that case? Well, I'm going to represent the box as a dot, okay? One of the forces that is on the box is the weight force. The weight force would be mass times gravity. So 3, which is the mass, times 10, which is the acceleration due to gravity. So there's a downward force due to gravity of 30 newtons, okay? Now the box is sitting on on the floor, and so the normal force from the floor is going to point upward. F sub n points upward. Okay, so now how do the sizes of these two forces compare? Well, let's do a little thought experiment. What if the normal force was bigger than the weight force? What would that mean for the normal force to be bigger than the weight force? Well, that would mean that the object is sitting on the surface. Normal force is bigger than weight, so it would actually accelerate up into the air. Okay? When you set something on the ground, do they randomly accelerate into the air? No. Okay? What would happen if the weight force was bigger than the normal force? Then that would mean that the box would accelerate through the floor into the ground. Okay? So the only thing that really makes sense for something that's just sitting on a surface is for these two to be equal. Okay? So in this case, the normal force is 30 newtons. Okay? So the takeaway for this example is that if a box is on a flat surface, with no other force besides gravity, then you're going to have that the weight force is equal to the normal force. Okay? But let me give you some other examples where the weight force is not equal to the normal force. Okay? So what if we had this same box, okay? But in addition to gravity, I was applying an upward force of 10 newtons. So I apply an upward force of 10 newtons, okay? In that case, what is the normal force going to be? Well, we would still have the weight force going down, which is 30 newtons, okay? We have a 10 Newton applied force, so that might be me lifting up on the box. So we have a 10 Newton upward force, okay? And then we have the normal force going upward again. And again, what happens if the amount of upward force is greater than the amount of downward force? Well, in that case, we would have the box jumping up into the air. If we have more downward force than upward force, then the box is going to get crushed into the ground. So the only sensible option is for the upward force to equal the downward force. So you can see that the normal force would have to be 20 newtons in this case. Why is that? Well, that makes the total upward force 20 newtons and then 10 newtons. So that would make the upward force equal to the downward, which is 30. Okay? So this is an example where normal force is not equal to weight. Let me give you another example. What if we had a wall? Okay. And again, it's this 3 kilogram box. Let me zoom in. So again, we've got this 3 kilogram box, and I'm pushing the side of the box with 50 newtons of force. All right. So what are the forces on the box in this case? Well, it's got the 50 Newton applied force. It's got the weight force that goes downward. That's 30 newtons. And then it has the normal force, which points away from the surface, which might be the wall. So we have the normal force. Okay. Now, in this example, the weight force is not pushing the box into the wall, okay? So the normal force doesn't care about this 30 Newton force because it's in the wrong direction. It's not forcing the box into the wall, okay? What the normal force does care about is this 50 Newton rightward force. What the 50 Newton rightward force is doing is it's pushing the box into the wall. So what would happen if the normal force were less than 50 newtons? Then that would mean that the box would be getting shoved inside the wall. It would accelerate inside the wall. So the only sensible option is for these two forces to have the same size. Okay? So that means that in this case, the normal force would have to equal 50 newtons. Okay? Let me give you another example with the normal force. What if you have something that is in an elevator? Okay? What if we have a 30 kilogram box in an elevator accelerating up at 7 meters per second squared. Okay? So here's the elevator. Okay? And here is the 3 kilogram box that is in the elevator. Okay? It's sitting on the floor of the elevator. One of the things you might notice if you ride an elevator is that you push the button to which floor you want to go to, and when the elevator starts moving, you can feel it, right? What you're feeling is the acceleration of the elevator. You're feeling the change in the normal force on your feet, okay? So what's going to happen in this case? Well, we have, and by the way, this is accelerating upward at 7 meters per second squared, okay? So we've got the normal force that goes upward, okay, because it's perpendicular to the floor. And we've got the weight force that goes downward. It's 30 newtons. Okay. So you might notice that I've drawn the normal force as bigger than the weight force in this case. Now, why is that? If the normal force is not bigger than the weight force, then how can the box accelerate upward with the elevator? The box would get left behind, right? The only way for the box to be moving with the elevator is for it to have the same acceleration as the elevator. Okay, so anyways, the normal force would have to be bigger than the weight force in this case. All right, and so we can actually do that we can actually calculate the normal force with Newton's second law. Net force equals ma. Okay, the net force is the positive force, which is normal, minus the downward force, which is weight, and that equals ma. So 3 times 7, 3 times positive 7. Type it into the live chat if you think you know how this would change if the elevator was instead accelerating downward. Okay, but that's 28, and then I add 30 to the other side, and I get that the normal force would be 58 newtons in this case. All right. One interesting thing is if you step on a scale. Oh, very good. Someone said that, yeah, the acceleration would be negative if the elevator is accelerating downward. Okay. Scales do not actually read your weight. A scale does not read your weight. What a scale reads is the normal force. Okay. A scale reads the normal force. Does your weight change if you jump up and down? No, it doesn't, right? You're still the same person. Your m times g is the same if you jump up and down. But if you jump up and down on a scale, the dial is going to be going like crazy. That doesn't mean your weight is changing. It just means that the scale is not measuring what you think it's measuring. What it's measuring is the normal force. Okay? If you're jumping up and down, your normal force is changing, but your weight force is not. Okay? The only time you can use a scale and have it truly read your weight is if you have something like a box that is on a surface, a flat surface that is not accelerating. Okay? So in order to use a scale properly, you need to stand on the scale and be at rest on a flat surface. Okay? The next force I want to talk about is called the elastic force. Which I will call F sub E. All right. And the elastic force is the force from a rubber band or a spring or anything that is flexing and provides resistance to that flexing. Okay? So that is an example of the elastic force. It is a resistive force. Okay? So the elastic force, if you stretch something, see, naturally I don't have anything that's elastic around me right now, so I'm giving this lesson. If I take this piece of paper, this piece of cardboard, and I try to flex it down, it fights me. The elastic force is upward because it wants to pop back up and be straight again. Okay? So the elastic force, it's resistive. If I push upward, the elastic force is trying to make the cardboard flex back down. So basically what the elastic force tries to do is it tries to get things back to a certain position. All right? The elastic band in underwear, okay? Why does it hold on to your waist? It's because the natural circumference of the elastic band is slightly less than your waist. So when you put on the underwear, it stretches out, and it's trying to stretch back to its original state. And so that provides a force which holds it onto you. So the formula for the elastic force is F sub E equals K times X, where K is called the stiffness. Okay? So, you could have different rubber bands that are made of different materials. You could have a super thick rubber band, you could have a thin rubber band, you could have rubber bands made out of different types of rubber. So all those things affect the stiffness, okay? So the stiffness is a property of the band, or of the material, I should say. The same material. And the units of stiffness are newtons per meter. X is the extension of the band. Okay, so how much is it stretched? How much is it flexed? Okay, now one thing about rubber bands is that they have a natural length. Okay, so by the way, units of extension would be meters. It's the amount that it is stretched. So let's suppose I have a rubber band, and here are the two ends of the rubber band. This rubber band, okay, would exert an elastic force of 0 because it's not taut, okay? So there's no elastic force because the rubber band isn't being stretched. Now, what if I took the two endpoints of the rubber band and I moved them apart? Well, eventually, I would get to the point where the rubber band is taut, but not stretched. Taut, but not stretched. So this has an elastic force of 0. This has an elastic force of 0 because it's taut, but it's not stretched yet. But if we go beyond that and we stretch it, okay, now we're going to have an elastic force that is not equal to 0. It's actually going to, so we stretched it beyond its natural length. So the extension is the amount stretched beyond its natural length. Okay? So if you have a rubber band that has a natural length of 10 centimeters and you stretch it so that the total length is now 21 centimeters, type it into the live chat if you know what would be the extension. If you have a rubber band with a natural length of 10 centimeters, so this distance is 10 centimeters, but then you stretch it so that this is total length is now 21 centimeters, what would you plug in for x in this equation? Okay. And while someone types in an answer for that, let's do an example. Oh, excellent. 11 centimeters. Very good. The elastic force is how scales work. Okay? So this example is going to be a scale. So what if a scale is a rubber band of stiffness, let's say 80 newtons per meter. Okay. You put, and let's say it has a natural length of 0.5 meters. Bug, knock it off. Get in here. What the heck are you doing? What the heck are you doing? You're making too much noise. You're making too much noise. Can I get a num-num? Num-num. 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 Give me a num-num. Can I get a num-num? Thank you. Just got rejected, basically, by my dog. Hazel appearance.
Hello, Hazel. Hello. What you do? What you do, Hazel? What you do?
Good girl.
Okay.
Back to the lesson. Okay. So you put let's say again, we'll stick with our three, actually, you put an object on the scale and its total length is now 0.7 meters. What was the mass of the object? Okay, so this is how a scale works. You put an object on the scale, it deforms, and the amount that it deforms tells you the mass of the object. The more massive the object is, the more it's going to deform. All right? So kind of the picture you want to have in your head is, here's the thing that's holding the top of the scale, and then you have a rubber band, and the rubber band has like a little bucket at the bottom, and in that bucket you have some stuff, okay? And so the total length of this is 0.7. Now let's analyze this object that is in the scale. The object that is in the scale is being pulled upward by the elastic force. Okay? And it's being pulled downward by the weight force, mg. Okay? Now, the only thing that makes sense here, when you put things on a scale, is the scale moving? It might bounce at first. You know, if you drop something on a scale, it might bounce at first. But eventually it just comes to rest on the scale. You see what I'm saying? So it's not moving, and if it's not moving, its acceleration is 0. Okay? So the only thing that makes sense here is for elastic force and weight force to balance each other. Because if one was bigger than the other, the thing that's on the scale would be accelerating up or down. Okay? So the equation is F sub E equals mg. These two forces are balancing each other. Now F sub E, the elastic force, is kx. And for x, we're going to use the distance beyond its natural length. So it's 0.5 meters long, but it's now 0.7 meters long. So the amount that it stretched was 0.2. The stiffness was 80. And gravity is 10. So 80 times 0.2 is 16. Divide both sides by 10. We get that the mass is 1.6 kilograms. All right. We're going to learn about one more force. So this is, and this one's the trickiest. SL 928. Part 2. This is the friction force. Friction is typically denoted by a script F, okay? And it is, the way friction works is it is an oppositional force. Oppositional force that is parallel to the surface. Okay? So what do I mean by that? Well, I mean that if you have a box that's on the floor, for example, and I push the box, if I push the box on this side, so I'm pushing the box to the right, friction is going to point to the left. Okay? It opposes what I'm trying to do to it. If I push on this side so that I'm pushing, I'm trying to push the object to the left, then friction is going to fight me and be a force to the right. Okay? So it's parallel to the surface, and it could be in any direction, whatever direction is opposing the motion. Okay? Similarly, if I wanted to make this object slide into the page, so I'm pushing it into the page so that it's going towards, towards you guys into the page, then the friction force is going to point out of the page to resist that. All right? There are two types of friction. There is static friction, okay, and there is kinetic friction. Kinetic friction is the friction that you have while something is sliding. Okay? Static friction is the friction that you get before sliding. Okay? So let me give you an example. I'm going to tilt my table down. And so I've got my coffee mug on a coaster. Okay? Now if I push, now I'm pushing on the coaster right now, but the cup is not moving. So because the cup is not moving, I'm pushing and static friction is fighting against me. Okay? But what if I push it, and I push it hard enough that it starts to slide? While it is sliding, I am fighting against what's called kinetic friction. Kinetic means motion. Okay? So static friction is the force that must be overcome to make something budge. Okay? The force that must be overcome to make something budge. Kinetic friction is the force that must be overcome to make the object slide. To make it, I should say, to keep it sliding. Okay, that is kinetic friction. There's a formula for kinetic friction. So kinetic friction is F sub K. And it is equal to mu sub K, this is the Greek letter mu, times the normal force. Okay? Mu sub K is called the coefficient of kinetic friction. And it is a constant that depends on how rough the surface is. So, for example, ice is very slippery. It has low friction, so it has a low coefficient of friction. Okay? Friction depends on the normal force. Why is that? Well, if I rub my hands together, the resistance you feel is kinetic friction. Okay? Now, I'm just pushing my hands together lightly right now, so it's easy to rub my hands together. But what if I use my strength and I really push my hands together? What force am I increasing? Well, I'm increasing the normal force, and now if I try to slide my hands across each other, it's really difficult. There's a lot of heat generated, okay? So similarly, if you have something that's really heavy on the ground, it's going to be hard to slide it because the normal force is bigger, okay? So the coefficient of friction is telling us about the intrinsic roughness of the surface. How rough is that interface? And the normal force is talking about how much are those two surfaces shoved together. All right. Now, let's talk about the force of static friction. Static friction is denoted by F sub S, and there's a maximum value that the static friction can have, and that is mu sub S times normal. Okay, now there's a little bit of a subtlety here. Why is that the maximum value? Well, if you just have something sitting on a table like this, there is no frictional force acting on it. Why is there no friction force acting right now? It's because nothing is trying to move the cup. As long as nothing is trying to move the cup, there's no friction, okay? But if I then come in and I push on the coaster, now static friction is going to activate, okay? So static friction is sort of responsive to how hard the person is pushing on the object, okay? So let's do an example. What if we have again, let's go to this 3 kilogram box. Okay, and the 3 kilogram box is going to have an applied force pulling it to the right. Okay, and if there's an applied force pulling it to the right, friction is going to point to the left. Okay, it also has a normal force going up and it has a weight force going down. The weight force is going to be 30 newtons. Okay? And let's suppose that for this particular surface, hang on one second, class. I hear eating, and I'm worried that Hazel is eating someone else's breakfast. That was a sanctioned food activity. So let's suppose that for this surface, the coefficient of static friction is 1.0. Okay. And the coefficient of kinetic friction is 0.5. Okay. So for this problem, the normal force would have to balance out the weight force. Why is that? Because if the amount of downward force were different from the amount of upward force, this box would not be sliding across the surface. It would be jumping into the air, into the ground. Okay? So the normal force is 30 newtons. Now that's going to allow us to calculate static friction and kinetic friction. So for static friction, the coefficient of static friction is 1.0. So I have 1 times 30 equals 30 newtons. Okay. Kinetic friction is going to be 0.5, because that's 0.5 times 30, which is 15 newtons. Okay. So we're going to have two examples here. The first example is, what if the applied force is equal to 20 newtons? All right. Well, how much force is required to make the box budge? That's static friction. So static friction is the force that must be overcome to make the object budge, to start to move. Okay. How much force, what is the maximum static friction? What is the biggest value static friction can have? 30. So could static friction equal 20 newtons? Yes, because 20 is less than 30. Okay. So if you apply 20 newtons to the box to pull it, but static friction goes up to 30, it's not going to move. Okay. So you're going to have no motion. Okay, but what if F sub A is equal to 40 newtons? 40 newtons is bigger than 30, so we've overcome static friction, so the box is going to start to move. And once it starts moving, so basically the box starts to move. And because the box started to move, we now have kinetic friction, okay? So that means that the friction is going to be 15 newtons. And the applied force is 40 newtons. So who can tell me what is the net force on the box in this case, if we have 40 newtons to the right and 15 to the left? Okay, so if I go to Newton's second law, net force equals ma. Well, the mass of the box is 3. And is anyone going to tell me what the net force is? Good, 25 newtons. So we got 40 to the right, 15 to the left. That's 25 newtons is the net force. Divide both sides by 3. So that is, 8.33. So you would have an acceleration of 8.3 meters per second squared. All right. So that's my lesson for today. And let's go ahead and transfer over to the Zoom room.